Imagine looking up at the night sky and realizing every tiny point of light is in the middle of its own journey. Some are just beginning to burn, some are steady and calm, some are already nearing their final breath. From our distance, they all look the same, quiet, distant, harmless. But inside, they are folding and fusing matter, bending space, and setting the rhythm for entire galaxies. Tonight, we're going to follow that path, how a star is born from cold clouds, how it lives its long, bright life, and how it ends in silence or in violence. If you enjoy exploring space at this slower pace, a soft like and subscribe helps this small corner of the universe keep glowing. Now, let's begin with the first spark. When we observe the night sky, the constellations appear fixed and immutable, granting the impression that stars are eternal fixtures of the universe. However, this perceived permanence is merely a consequence of the immense difference between the human lifespan and the stellar timescale. In reality, stars are not static objects. They are dynamic entities that undergo a profound series of physical metamorphoses. Every star possesses a definite beginning and an inevitable conclusion. They emerge from chaotic regions of cold gas and dust, ignite to release vast amounts of energy for millions or billions of years, and eventually cease to function, often destroying themselves in the process. To understand this cycle, we must first examine the locations where these celestial bodies come into existence. Across the galaxy, there are vast reservoirs of matter known as stellar nurseries. These are nebulae, gigantic clouds primarily composed of molecular hydrogen and dust particles. While some of these structures are relatively modest in size, others are colossal, stretching across tens or even 100 light-years of deep space. Within these clouds, the dominant force is gravity. It works inexorably to draw distinct particles together. As gravity pulls gas and dust inward, the material becomes compressed. This compression increases the internal temperature and pressure, setting the stage for nuclear ignition. Most of these molecular clouds are dark and cold, barely distinguishing themselves against the background vacuum of space. However, under specific conditions, the radiation from nearby massive stars can energize the gas, causing the nebula itself to glow. Some of these illuminated structures are vast enough and bright enough to be observed from Earth without the aid of telescopes. A primary example of this phenomenon is located roughly 1,344 light-years away from our solar system. This is the Orion Nebula. To an observer on Earth, looking at the Orion Nebula means seeing light that began its journey over a millennium ago, traveling through the interstellar medium to reach us today. In the night sky, this nebula forms the central point of the feature, often referred to as the Sword of Orion, appearing as a fuzzy patch of light in a line of three relatively bright sources below the prominent belt of the constellation. Because of its significant size and its proximity to Earth relative to other star-forming regions, the Orion Nebula has served as a crucial laboratory for astronomers. It allows for the direct observation of stellar evolution processes that would be impossible to resolve in more distant galaxies. Since the early days of telescopic astronomy, it has remained one of the most rigorously studied objects in the celestial catalogue. In 1993, the Hubble Space Telescope provided some of the first high-resolution images of this region, stripping away the blurring effects of Earth's atmosphere. These observations revealed a complex topography of gas and dust, illuminated in a rich spectrum of colors. The visual data showed that much of the nebula radiates in hues of red and bluish purple. These colors correspond to the specific wavelengths of light emitted by hydrogen gas when it is excited by ultraviolet radiation. However, earlier spectral analysis of the nebula's outer regions revealed a puzzling anomaly. Astronomers detected distinct, bright green spectral lines that did not correspond to any chemical element known in laboratories on Earth. This mystery persisted for a significant period. The distinct green fingerprint led to a hypothesis that space might contain a unique element not found on our planet. Scientists tentatively named this hypothetical substance nebulium, theorizing it was a fundamental component of celestial clouds. As our understanding of atomic physics advanced, however, the true nature of this light was revealed. It was not a new element, but a familiar one, behaving in an unfamiliar environment. The green emission is produced by oxygen atoms that have lost 2 of their electrons due to intense radiation, a state known as doubly ionized oxygen. On Earth, the atmosphere is too dense for oxygen to remain in this state long enough to emit this specific green light. The atoms collide and lose energy before the emission can occur. In the near vacuum of the nebula, however, the density of gas is incredibly low, millions of times less dense than the best laboratory vacuum. This extreme rarefaction allows the oxygen atoms to remain undisturbed, long enough to release photons at this specific wavelength. This discovery was pivotal, as it explained the illumination mechanisms not just in Orion, but in planetary nebulae throughout the universe. Within the boundaries of the Orion Nebula, the process of star formation is active and ongoing. Current surveys have identified no fewer than 3,000 individual stars within this region. Alongside these formed stars are massive reservoirs of interstellar gas and a multitude of protostars objects in the earliest phase of gathering mass, not yet fully ignited. This entire assembly of matter is concentrated within a volume spanning approximately 23 light-years in diameter. It is a gravitationally bound ecosystem where the radiation and stellar winds from newborn stars continuously shape and redistribute the remaining gas and dust. The total mass contained within this region is substantial. Estimates suggest the material here equals roughly 10,000 times the mass of our Sunday. When analyzing the structure of the nebula in detail, specific subregions become apparent. The most significant of these is located at the very heart of the cloud. This is the trapezium cluster, technically designated as Theta-1 Orionis. It is an open cluster of stars, remarkably young in cosmic terms. While our Sun is roughly 4.6 billion years old, the stars in the trapezium are estimated to be only about 300,000 years old. They have essentially just been born. The cluster consists of 8 primary components, tightly packed together. Several of these are binary systems, where 2 stars orbit a common center of mass, while others are solitary. The core of the cluster is dominated by 4 extremely bright stellar systems. These are arranged in a trapezoidal pattern, which gives the cluster its common name. These 4 systems are separated by relatively short distances, all residing within a sphere of space measuring only about 1.5 light-years across. To understand the density of this cluster, one might compare it to the Sun's neighborhood, where the nearest star is over 4 light-years away. Here, massive stars are crowded into a much smaller volume. The mass of each of these primary stars ranges between 15 and 40 times the mass of the Sunday. In stellar physics, mass dictates destiny. Objects with this amount of mass burn through their fuel at a voracious rate, resulting in high surface temperatures and extreme luminosity. The most dominant member of this group is Theta-1 Orionis C. It is the anchor of the cluster, possessing the greatest mass and the highest brightness of any star in the entire nebula. Theta 1 Orionis C is a blue main sequence star. Its mass is calculated to be approximately 40 times that of the Sunday. Physically, it is much larger than our star, with a radius 8 times greater. The surface temperature is equally extreme, measuring approximately 45,000 degrees Kelvin. For comparison, the Sun's surface is roughly 5,500 degrees Kelvin. This immense heat results in a luminosity that is difficult to comprehend. Theta 1 Orionis C emits about 250,000 times more energy than the Sunday. The influence of this single star shapes the entire environment around it. The ultraviolet radiation it generates acts as a floodlight, illuminating the vast clouds of the nebula. However, in the immediate vicinity of the star, the space is surprisingly clear of gas. This is due to the physical pressure of light and particles. Objects of this mass and temperature generate an exceptionally powerful stellar wind, a stream of charged particles moving at high velocities. This wind exerts force on the surrounding medium, blowing the rarefied gas and dust outward and carving out a cavity in the nebula. Moving outward from the central trapezium cluster, we encounter other significant stellar groupings. Located a few light-years away is the system known as Theta 2 Orionis. This system consists of 3 stars that are gravitationally bound to one another. They are situated near a prominent, linear feature of the nebula called the Orion Bar. The Orion Bar is effectively a wall of dense gas and dust, where the ionization front from the massive stars meets the colder molecular cloud. For years, studying the stars in this specific region was challenging because they are shrouded in thick veils of dust that block visible light. Recent advancements in infrared astronomy, particularly through the capabilities of the James Webb Space Telescope, have allowed astronomers to peer through these dust curtains. The infrared wavelengths penetrate the clouds, revealing the details of the Theta 2 Orionis system. The primary component of this system is a massive star, only slightly smaller and less luminous than the giant in the trapezium. Its surface temperature is measured at approximately 35,000 degrees Kelvin. The second component of Theta 2 Orionis is also a giant in its own right, with a mass 15 times that of the Sunday. It shines with a brightness 12,000 times greater than our solar output. The third member of this trio is smaller, but still significant, holding a mass equal to 5 suns and possessing a surface temperature of nearly 14,000 degrees Kelvin. These massive, blazing stars dominate the energy output of the region. However, as astronomers analyzed the data from this chaotic nursery, their attention was drawn away from these brilliant giants to something far more subtle, hidden in the dust. While the massive giants dominate the visible light spectrum, the deployment of the James Webb Space Telescope has fundamentally altered our understanding of this region. Its advanced infrared sensors possess the capability to penetrate the dense, obscuring veils of gas and dust that block optical telescopes. By peering into these opaque clouds, the telescope detected objects that were previously invisible to human observation. Within the dense heart of the Orion Nebula, astronomers have identified approximately 180 specific structures known as proplids. The term proplide is a shorthand designation for an ionized protoplanetary disk. These are dense, dark concentrations of matter surrounding a central star that is still in the volatile process of formation. These disks are the raw material for future solar systems. One specific example that offers a clear view of this process is the object designated Orion 294-606. This is a protostar in the very early stages of its life, estimated to be roughly 1 million years old. It is encircled by a vast disk of gas and dust with a diameter of approximately 300 astronomical units. To put this scale into perspective, 1 astronomical unit is the distance from the Earth to the Sunday. Therefore, this single disk spans a width 300 times greater than the distance between our planet and our home star. Because of its favorable orientation relative to Earth, astronomers can analyze its structure and dimensions with high precision. Projections indicate that within a few million years, this central object will stabilize and enter the main sequence phase, becoming a fully functioning star. As it matures, the surrounding disk will likely condense into a system of exoplanets, potentially accompanied by their own moons. If one were to stand on the surface of a future celestial body within this system, the night sky would present a spectacle vastly different from what we view from Earth. Because this system resides inside a dense cluster, the sky would be filled with a multicolored luminous veil, the remnants of the nebula itself. The viewer would see a multitude of nearby stars, far more numerous and brilliant than the scattered points of light visible from our own planet. Occasionally, this alien sky would be dominated by tremendous swirls of glowing gas, illuminated by the radiation of massive neighbors. These bright gas clouds would reflect enough light to turn the deepest night into a translucent twilight, blurring the line between day and night. However, if we expand our view beyond these individual systems to the wider region, the dynamics of the nebula become even more complex. The bulk of the nebula's volume is not empty. It is filled with scattered gas in constant motion. The central core of the cloud consists primarily of highly ionized hydrogen. Here, the atoms have been stripped of their electrons by the intense ultraviolet radiation from the massive stars we observed earlier. This gas absorbs high-energy stellar radiation and re-emits it, maintaining a temperature that can reach 10,000 degrees Kelvin. However, this thermal profile is not uniform. As one moves toward the periphery of the region, the temperature drops sharply. These extreme contrasts in temperature and pressure, combined with the physical impact of stellar wind streams, act as an engine for atmospheric motion. They drive the material into tremendous currents and turbulent vortices. Mathematical models and calculations suggest that some of these gas currents achieve velocities of up to 50 kilometers per second. The scale of these vortices is immense, with some individual swirls exceeding the size of our entire solar system. In other specific zones of the nebula, instruments have detected thin strands of matter stretching for several light years. Analysis shows these strands consist of relatively cool molecular hydrogen, distinct from the ionized gas in the center, and notably lacking in complex compounds like methane, ethane, or water. Moving further outward, we observe that the energetic central region of the Orion Nebula is enveloped in a much larger shell of cooler, denser gas. Here, the visual data presents a complex layering effect. The brilliance of the young stars and the luminescence of the ionized hydrogen intertwine with the dark, cold clouds. This interaction creates a phenomenon often described as a multicolored curtain of light, where emission and absorption occur simultaneously. Behind this curtain lie hundreds of stellar objects that remain invisible in the optical range. Yet, the infrared capabilities of modern observatories allow us to see through the veil of interstellar matter to count the population hidden within. By synthesizing data from multiple wavelengths, astronomers have catalogued approximately 700 protostars at various stages of evolution within this outer region. The concentration of stars here is noticeably lower than in the central trapezium area. This difference in population density is directly related to the lower degree of gravitational compression in the outer interstellar gas. Where gravity is weaker, fewer stars are born. The absolute majority of these objects are extremely young by cosmic standards, captured in the very midst of their formation process. To understand what is happening here, we must look at the modern concepts of stellar evolution. A new star begins to form when a large cloud of interstellar gas undergoes gradual gravitational compression. The cloud collapses under its own weight. Typically, this is not a uniform process. As the giant nebula contracts, it fragments into a number of closely grouped centers of gravity. Each of these centers becomes a seed that will soon transform into a protostar. These clusters of activity are what astronomers refer to as stellar nurseries, or more formally, regions of star formation. The collapse continues until a critical threshold is reached. At a certain point, the internal pressure of the compressed gas rises enough to counteract the inward pull of gravitational forces. This brings the protostar to a state of temporary hydrostatic equilibrium. It is not yet a full star, but it is stable. During this phase, the material that has not fallen into the star swirls around it, forming a giant vortex disk. Some of this material spirals inward and is gradually absorbed by the future star, adding to its mass. The rest of the material, by contrast, is expelled far beyond the boundaries of the nascent system. This expulsion is driven by complex magnetohydrodynamics. As the young star rotates, it generates a powerful magnetic field. Ionized particles are captured by these magnetic field lines, accelerated to extreme velocities, and then ejected from the poles of the star. Calculations indicate that these bipolar outflows can reach speeds of several hundred kilometers per second. When these high-speed jets collide with the slower, denser gas clouds surrounding the star, the impact creates large-scale shock waves. These collision zones form distinct structures known as Herbig-Haro objects. In this process, the kinetic energy of the fast-moving jet is instantly converted into thermal energy and light, causing the gas to glow. This dissipation of energy gives these bizarre structures their vibrant and varied colors, which correspond to different elements being excited by the shock. Furthermore, the ultra-fast motion of the jets affects the surrounding material, spreading shock waves outward that can be captured by telescopes. Since stellar nurseries contain many closely spaced protostars, and each protostar can produce multiple gas emissions, the environment is chaotic. It is not surprising that Herbig-Haro objects exhibit an amazing variety of shapes and colors, as they are essentially the debris of major cosmic collisions. These objects are defined by their instability. Herbig-Haro objects change color and shape rapidly on human timescales and are transient features. Typically, they disperse completely over a period of several tens of thousands of years. During this brief lifespan, the material within them travels between 1 and 3 light-years on an escape trajectory from their parent stars. To date, approximately 400 such objects have been discovered, though estimates suggest the total number within the Milky Way galaxy could be around 150,000. Among the varieties of this phenomenon, there is a specific type detected in the Orion Nebula known as bullets. These are compact clumps of gas, hundreds of astronomical units in diameter. They move at incredible speeds, possessing enough kinetic energy to easily pierce through thinner hydrogen clouds. As they travel, they create far-flung wakes and shock waves, similar to a vessel moving through water. Spectral analysis of these bullets reveals that their frontal zones, the tips of the projectiles, contain atoms of iron that glow brightly in the infrared spectrum due to the heat of friction. These iron bullets are estimated to be approximately 1,000 years old. Despite detailed study, their precise origin remains a subject of scientific debate. The prevailing hypothesis suggests they originated from a catastrophic explosive event deep within the nebula that flung material outward like shrapnel. Expanding our field of view significantly, we find that the Orion Nebula is merely one component of a much larger cosmic structure known as the Orion Molecular Cloud Complex. This massive assembly stretches for hundreds of light years, accounting for virtually the entire constellation of Orion as seen in Earth's night sky. Within this vast complex, other iconic structures exist. This is the location of the Horsehead Nebula, remarkable for its distinct, silhouette-like shape. The Horsehead is a dark nebula, a dense cloud of dust approximately 3.5 light-years in diameter. It produces no light of its own, but is clearly visible because it blocks the light from the contrasting scarlet glow of the hydrogen gas behind it. Also located near the Orion Nebula is an impressive arc of emission known as Barnard's Loop. This is a faint emission nebula, immense in scale, measuring about 300 light-years across. Its origins trace back approximately 3 million years. The loop is believed to be the result of a series of consecutive supernovae explosions of massive stars that lived and died in close proximity to one another. The shockwaves from these detonations compressed the surrounding gas, and as these jets mixed together, they produced a gigantic, curved shell. The reddish hue of the loop is maintained by the ionizing glow of several young stars gathered in a nearby open cluster. For all its structural grandeur and visual beauty, the Orion Nebula is, by the standards of the universe, a fragile and temporary object. The very stars it creates are the agents of its destruction. The intense stellar winds and the pressure of photon radiation from the many young stars, combined with the violent gas emissions and turbulent vortices, are constantly pushing the nebula's material away. The nebula is evaporating. It has already lost approximately 60% of its original mass to this dispersal process. Projections suggest that in about 100,000 years, the gas will be largely stripped away. The shining, multicolored cloud will vanish. In its place, there will remain an open star cluster, physically similar to the well-known Pleiades. For a time, the young stars that form together will move together through space, bound by their mutual gravity. However, this bond is temporary. Eventually, the rotation of the galaxy and gravitational interactions with other objects will loosen the cluster. Each star will find its separate path, drifting away to navigate the vast expanse of the boundless galaxy alone. As these stars drift apart and settle into their independent trajectories within the galaxy, their destinies are already written. According to current astrophysical concepts, the life cycle and ultimate fate of any star are determined almost exclusively by a single variable, its initial mass. This mass dictates how much fuel the star possesses and, more importantly, how quickly it burns through that reserve. For the vast majority of stars in the universe, the ending is quiet. If a star possesses a mass that is less than 8 times the mass of our Sun, it lacks the gravitational pressure required to fuse elements heavier than carbon and oxygen. Once such a star completes its evolutionary stages and exhausts its nuclear fuel, the outer layers are gently cast off, leaving behind the exposed core. This remnant is known as a white dwarf. It is a stellar ember, roughly the size of Earth, but containing the mass of a star, held up against gravity not by thermal fusion, but by the pressure of electrons refusing to occupy the same energy state. Over time, a white dwarf will radiate its remaining heat into the vacuum of space. It is assumed that after billions of years, it will lose all its thermal energy and cease to emit light, transforming into a hypothetical object called a black dwarf. This process takes an incredible amount of time, longer than the current age of the universe. Therefore, while we can predict their existence, no black dwarf exists yet. This quiet fading is the path destined for more than 99% of the stars in the universe, including our own Sunday. However, for the rare celestial bodies where the mass exceeds 8 solar masses, evolution follows a drastically different and more violent trajectory. In these massive stars, the pressure is sufficient to fuse heavy elements up to iron. Once an iron core forms, energy production stops abruptly, and gravity instantly wins the battle against internal pressure. The result is a catastrophic collapse, followed by a supernova explosion. In a fraction of a second, the outer shells of the star are blasted into the surrounding space at velocities reaching thousands of kilometers per second, eventually forming a scattered gas nebula rich in heavy elements. Yet, the most significant transformation occurs at the very center of the explosion. There remains a supercompact and extremely dense object, the former stellar core. The fate of this remnant, like the star before it, depends entirely on how much mass remains after the explosion. If the remaining mass is excessive, specifically, if it exceeds the theoretical limits of matter's structural integrity, the core will not be able to resist the inexorable pull of gravity. It will inevitably collapse in on itself completely, vanishing from the visible universe to become a black hole. However, there is an intermediate possibility. In cases where the mass of the stellar remnant falls within the specific range of 1.4 to 2.2 solar masses, the collapse is halted by quantum forces. The result is the formation of a neutron star. Inside this object, the gravitational forces are so intense that they crush the atomic structure itself. Electrons are forced into protons, merging to become neutrons. The empty space within the atom is eliminated, resulting in a super-dense form of neutron matter with physical properties that defy earthly comparison. Studying these objects presents significant challenges for astronomers. Firstly, celestial bodies of this class are extremely rare compared to standard stars. Statistical calculations indicate that there is likely only one neutron star for every 1,000 ordinary main sequence stars. Secondly, despite their immense mass, they are physically tiny and possess a very small surface area. Consequently, they emit very little light in the optical range, making them virtually invisible to traditional telescopes. Therefore, before the advent of space-based observatories capable of detecting high-energy X-rays, it was effectively impossible to spot these objects against the black background of space. It is not surprising, then, that the first neutron star was discovered relatively recently, in 1967. This was several decades after theoretical physicists had calculated their existence on paper. The discovery was made possible largely due to an unusual phenomenon associated with the fundamental law of physics known as the conservation of angular momentum. To understand this, one must picture the original star. It may have been millions of kilometers in diameter, rotating slowly on its axis. When the core collapses into a neutron star, it shrinks to a diameter of only about 20 kilometers. Just as a figure skater spins faster when pulling their arms in, the collapsing core accelerates its rotation to extreme speeds to conserve momentum. Thanks to this effect, most young neutron stars possess a very high rotational speed, spinning multiple times every second. Additionally, the collapse concentrates the star's magnetic field, making it trillions of times stronger than Earth's. The interaction of these intense magnetic and electric fields accelerates charged particles, generating powerful beams of radiation that blast out from the magnetic poles. As the star spins, these beams sweep across space like the light from a lighthouse. If the beam crosses the Earth, we observe it as a pulse. Such objects are called pulsars. Because this radiation is powered by the stable rotation of the star, the bursts are repeated with a very clear periodicity, making them some of the most precise clocks in the universe. These pulses are effectively detected by radio and X-ray telescopes, allowing us to locate them even at distances of thousands of light years. In total, more than 3,200 neutron stars have been discovered so far. The data suggests that about 90% of them are solitary wanderers, moving through the galaxy alone. The remaining 10% are part of binary or multiple systems. In these cases, the neutron star is gravitationally locked to a companion. Most often, the companion of these cosmic bodies is a bloated red giant or a standard main sequence star. However, in rare and isolated cases, the companion is another neutron star. This specific configuration occurs when two massive stars are born together, live their lives in tandem, and synchronously approach the end of their life cycles. The explosion of the first star creates a neutron star, and eventually, the explosion of the second triggers the collapse of the companion. Because of the loss of mass and energy during these transformations, the orbits can change drastically. The remnants of the stellar nuclei often converge closely, spiraling toward one another. As they get closer, the laws of orbital mechanics cause their mutual velocity to grow to enormous values. According to today's scientific concepts, this is exactly how the amazing system designated as PSRJ 737-3039 was formed. This system serves as one of the most extreme laboratories for general relativity known to science. It is located at a distance of about 4,500 light-years from Earth. It is quite unique because it is the only known system made up of two pulsars that are both active and detectable, located very close to each other. The physics at play here are staggering. The first component, often referred to as pulsar A, is approximately 1.34 times more massive than the Sunday. Despite this mass, it possesses an incredible speed of proper rotation. Every single second, this object completes 44 full revolutions around its axis. To visualize this, imagine a sphere the size of a city spinning faster than the blades of a kitchen blender. The second component, pulsar B, is slightly smaller and slower, though still extreme by any normal standard. Its mass is 1.25 times that of the Sun, and its rotation period is 2.77 seconds per revolution. If we want to take a closer look at these objects to understand their nature, we must first comprehend their scale. Their physical size is extremely small by space standards. Either component of the system is no more than a couple of dozen kilometers in diameter, roughly the length of Manhattan Island. However, as for their mass, it is comparable to that of most known stars. Packing the mass of the Sun into a sphere the size of a city has profound consequences. Due to these factors, the density of the matter that the pulsars are made up of is extremely high. A single teaspoon of this material would weigh billions of tons on Earth. In order to understand how matter behaves under these crushing conditions, we need to look deep into their interior structure. Since we cannot physically visit a neutron star, scientists rely on the use of advanced mathematical modeling techniques combined with the theory of nuclear physics. These models allow us to learn things not immediately visible to telescopes. The structure of a neutron star is stratified, much like a planet, but composed of exotic materials. The outermost layer of objects of this class is the atmosphere. Incidentally, for neutron stars, this concept differs significantly from the familiar sphere of gas that envelops a planet like Venus or the Earth. On Earth, the atmosphere extends for hundreds of kilometers. For both components of the binary system we are observing, this atmospheric layer is compressed by gravity to a thickness of no more than a few millimeters. This situation is typical for the absolute majority of mature neutron stars. However, the youngest and hottest objects of this class, which have not yet cooled significantly, may have a slightly more expanded atmosphere of several dozen centimeters. Regardless of thickness, this layer is made up of plasma, highly ionized remnants of stellar matter. Most of it consists of hydrogen and helium atoms left over from the star's previous life, but heavier elements like carbon are also to be found. Beneath this razor-thin atmosphere lies the next major layer, the outer crust. This is a solid shell that can be several hundred meters thick. The physics here is a battle between forces. The gravity in this region is intense, pulling everything toward the center. It is not yet strong enough to overcome the electrostatic repulsion between electrons and protons, meaning atoms still exist. However, the gravity is strong enough to destroy the usual structure of matter we see on Earth. The elementary particles are jumbled together into a super-dense, crystalline lattice. They retain their internal integrity as atomic nuclei, but they are packed tighter than steel. Several powerful forces are pulling on the outer crust at once. There is the inward crush of gravity, the intense grip of the magnetic field, the outward push of electrostatic repulsion, and the centrifugal inertia attempting to tear the star apart as it spins 44 times a second. This combination places the surface of neutron stars under constant, unimaginable mechanical stress. The crust is rigid, but it is not indestructible. Occasionally, the stress builds up to a breaking point. When the crust fractures, starquakes occur. These are titanic deformations of the surface of the cosmic object, analogous to earthquakes, but vastly more energetic. Because the gravity is so strong, the surface does not buckle by kilometers. Instead, mountains form that are only a few millimeters high and cracks open that are perhaps a centimeter wide. These numbers do seem insignificant to a human observer. However, we must consider the gravitational potential energy. At extremely high gravity, billions of times stronger than Earth's lifting material, even 1 millimeter requires immense energy. Therefore, a centimeter-high mountain on a neutron star represents a deviation in the gravitational field comparable to the height of Olympus Mons on Mars. When this crust snaps or shifts by a mere millimeter, it releases a blast of energy in the form of X-rays and gamma rays that can outshine entire galaxies for a brief moment. If we go still lower, beneath this solid, stressed crust, we will see that the geology changes. This layer has no clear boundaries. Instead, it transitions gradually as we go several kilometers deep into the neutron star. As we dive into its interior, the weight of the overlaying crust causes the pressure to increase exponentially. In this zone, the classical laws of atomic structure begin to fail completely. The pressure becomes so great that it overcomes the repulsion between particles. More and more electrons are pushed into the atomic nuclei. They have nowhere else to go. This initiates a process called inverse beta decay, where electrons react with protons to form neutrons. Matter itself is being fundamentally reorganized. As the pressure intensifies beyond the capacity of electron degeneracy, the protons capture the electrons. This fusion results in the creation of neutrons. However, This reaction also produces a byproduct, a highly elusive elementary particle known as a neutrino. Unlike photons of light, which can be trapped or absorbed by dense matter, neutrinos interact strictly through the weak nuclear force and gravity. This means they pass through normal matter as if it were empty space. Almost immediately after they are created, these particles stream out of the celestial body's interior at near light speed, carrying a tremendous amount of excess thermal energy with them. This neutrino cooling is the primary mechanism that allows the newborn neutron star to stabilize. Beneath the inner crust, we encounter the outer core. This region consists entirely of pure neutron matter. It is a superfluid state where neutrons are packed together so tightly that they effectively touch. The density here is incomprehensibly high, 10 to 15 times greater than the density of an atomic nucleus itself. To visualize this, imagine compressing the entire mass of planet Earth. For Earth to reach this density, its diameter of 12,700 kilometers would need to be crushed down to a sphere with a radius of only 150 meters. A single cubic centimeter of this material would contain several billion tons of mass. In both components of the binary system we are observing, this outer core likely extends all the way to the center. However, theoretical physics suggests that particularly massive neutron stars, those pushing the upper limits of stability, should possess a distinct inner core. The exact nature of matter at this depth remains a subject of intense scientific debate. According to one leading hypothesis, the pressure in the center of these massive objects becomes so extreme that it exceeds the structural integrity of the neutrons themselves. The neutrons dissolve. They break down into their constituent particles, up quarks and down quarks, forming a hypothetical state known as quark matter or quark-gluon plasma. An object dominated by this phase is theoretically termed a quark star. Other assumptions allow for the formation of hyperonic matter, which involves the creation of heavier, unstable particles called hyperons, or even kaon condensates. These represent bizarre states of matter with highly unusual physical properties that do not exist anywhere else in the visible universe. However, because we cannot look inside a neutron star, all these structures remain within the domain of hypothesis. Proving or disproving their existence requires data we do not yet possess. Expanding our view from the interior back to the system as a whole, we discover several surprising and intriguing facts about the dynamics of PSRJ 737 3039. First, we must analyze the orbital mechanics. Calculations confirm that the two pulsars in this system are orbiting a common center of mass. Their paths are moderately elongated ellipses, but the orbits are exceptionally compact. Observations show that the average distance between the two components is only 800,000 kilometers. To put this in perspective, the diameter of our Sun is approximately 1.4 million kilometers. This means the entire binary system, two stars heavier than the Sun, would fit comfortably inside the Sun itself with room to spare. Because of this dangerously small distance, the speed of mutual motion for both objects is extremely high. They hurtle through space at velocities exceeding 300 kilometers per second. Consequently, the pulsars complete a full revolution around their common center of mass in just 2 hours and 45 minutes. Such rapid motion of massive objects creates a laboratory for extreme physics. This system exhibits a number of unusual phenomena that can only be explained by Albert Einstein's general theory of relativity. For example, precise timing observations show an anomaly in the rotation of the pulsars. At the moment of maximum convergence, when the two stars are closest to each other, the period of proper rotation of each star temporarily increases by 38 microseconds. After they move apart, the rotation returns to its previous value. Classical physics cannot explain why a clock would run slower simply because it is near another object. However, the theory of relativity predicted this effect long before its practical detection. This anomaly is associated with relativistic time dilation. The immense gravity at the point of closest approach literally warps the fabric of space-time, causing time to pass more slowly for the star compared to an outside observer. Another phenomenon that stands out occurs during mutual eclipses, when one pulsar passes behind the other from our perspective. This is associated with an anomalous redshift detected in the spectrum of the signal. As the radio waves from the distant pulsar pass through the intense gravitational field of the foreground pulsar, they must climb out of a gravity well. This effort costs energy. Since light cannot slow down, it loses energy by increasing its wavelength, shifting toward the red end of the spectrum. Furthermore, the orbits themselves are not static. They are evolving. The point of the star's maximum proximity, known as the periastron, is constantly shifting its position in space. Imagine drawing an ellipse on a piece of paper, then rotating the paper slightly after every loop. This phenomenon is called relativistic periastron advance. It is usually recorded when studying fast celestial bodies orbiting massive objects. For example, in our own solar system, the planet Mercury exhibits this behavior. Mercury's orbit shifts by 43 arc-seconds every 100 years, a tiny amount that provided the first proof of Einstein's theory. However, the effect in the binary pulsar system is on a completely different scale. The periastron of this system shifts 140,000 times more strongly than Mercury's. Within a single year, the orbit rotates and deviates from its previous position by as much as 17 degrees. Thus, PSRJ 737-3039 holds the record for the highest relativistic shift among all stellar systems known to science. If we leave the dry figures for a moment and consider the possibility of other objects, we might ask about hypothetical planets hiding in this amazing system. The existence of planets here seems rather unlikely, though not strictly impossible. The formation of the system involved two massive supernova explosions. Any planets that existed originally would likely have been destroyed or ejected into deep space. However, it is possible that new planets could form from the debris fields left behind. Some objects far from the center might have had a chance to survive the crushing double explosion, or a second generation of planets may have coalesced later. Answering this question definitively is difficult because none of the widespread methods of searching for exoplanets, such as the transit method or radial velocity method, are effective for exploring such chaotic, high-energy environments. In any case, we cannot speak of the viability or habitability of any hypothetical celestial bodies here. The environment is sterilized by freezing cold temperatures far from the stars, punctuated by deadly beams of X-rays and gamma radiation. It is an inhospitable place. The future of this system is equally violent. Observations show that this binary pulsar is constantly generating gravitational waves. These are ripples in the very fabric of space-time, created by the acceleration of massive objects. Radiating these waves consumes energy. This energy comes from the orbital momentum of the stars. As they lose energy, they fall closer together. The distance between the two components is steadily decreasing by 7 millimeters every day. This phenomenon occurs in all physical multiple star systems, including the Earth and Sun, but usually the effect is too faint to be measured. Here, it is significant. This decay rate tells us that the system is doomed. In approximately 85 million years, the two pulsars will spiral in and merge together. The result will be a cataclysmic event known as a kilonova. They will likely collapse to form a black hole. This tremendous cataclysm will be the source of super powerful gravitational waves that will travel through the entire Milky Way and reach other galaxies far beyond it. The flash accompanying the merger may briefly become one of the brightest sources of radiation in the Earth's sky, even if it happens millions of years from now. It is in these moments of destruction that heavy elements like gold and platinum are forged and scattered into the cosmos. In any case, the echoes of this devastating explosion will eventually fade without a trace into the infinity of the universe. Leaving behind these extreme remnants of dead stars, we shift our focus to the more familiar environment of our own neighborhood. By galactic standards, the area of space located on the outer edge of the solar system is considered to be sparsely populated. It is a quiet suburb of the Milky Way. Still, sparse is a relative term. Approximately 50 stellar systems are known to be located within a radius of 15 light-years from the Earth. The population here is diverse. Some of these neighbors are single stars like our Sun, while others contain two components or more. When we account for these multiples, the total number of individual stars in this local volume reaches 65. Modern astronomy has revealed that many of them host their own families of exoplanets. Some even possess protoplanetary disks made up of gas and dust where the processes of celestial body formation are still in progress. In order to analyze this variety, we must map out the environment. As we slowly recede from our home planet, we will cover dozens of light years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light years away from the Sun, we reach our first significant stop. This is a small red dwarf designated as GJ699, but it is more commonly known as Barnard's star. Barnard's star is a subject of fascination for astronomers, not because of its size, but because of its motion. It is remarkable for its incredible travel speed across the sky. While all stars move, their great distance makes them appear fixed to the human eye over a lifetime. Barnard's star is different. It possesses the highest proper motion of any known star. It moves fast enough to cross a distance equivalent to the diameter of the lunar disk in the course of 180 years. This apparent speed is due to 2 factors: its actual high velocity through space and its close proximity to us. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second. Trajectory calculations indicate it is going to become our closest stellar neighbor in about 10,000 years, temporarily taking that title from the Alpha Centauri system. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. However, despite being so close, it will remain a ghost in the sky. The red dwarf is so dim that it will not be visible to the naked eye even at such a small distance. It will be possible to observe it only through optical devices like telescopes or binoculars. This dimness is a defining characteristic of its class. The star's mass is just 17% that of the Sunday. Physically, it is small. Its radius is 6 times smaller than that of our star, making it only slightly larger than the planet Jupiter. Just like all red dwarfs, Barnard's star is quite cool. Its surface temperature is measured at just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. This is roughly half the temperature of our Sunday. With these characteristics taken into account, it is not surprising that the object's luminosity is remarkably low. It emits light with an intensity 2,300 times lower than that of our parent star. Because of this low energy output, the habitable zone, the region where liquid water could exist, is located extremely close to the star. In the search for worlds beyond our own, the proximity of Barnard's star has made it a primary target for investigation. In 2018, a breakthrough occurred. The results of a comprehensive 20-year observation campaign were published, analyzing the minute movements of the star. These observations focused on the star's proper motion and radial velocity, the subtle wobble caused by the gravitational tug of an orbiting companion. The data provided compelling evidence for the presence of a planetary body. The calculations derived from this gravitational signature indicate that the object is a super-Earth. This classification refers to a planet with a mass higher than Earth's but lower than that of the ice giants. Like Uranus, specifically, this candidate planet has a mass of at least 3.2 times that of our home world. Designated as GJ699b, the planet orbits at a distance of approximately 0.4 astronomical units from the center of the system. This places it roughly at a distance comparable to Mercury's orbit in our solar system. It completes a full revolution around its parent star every 233 Earth days. For astronomers, studying this world presents a significant geometric challenge. Unfortunately, the orbital plane of the exoplanet is tilted in such a way that it does not pass directly between Earth and Barnard's star. Because no transit occurs, we cannot analyze the starlight filtering through the planet's atmosphere to determine its chemical composition. We are left in the dark regarding its specific makeup. However, by applying mathematical modeling based on the known physics of red dwarfs, we can construct a probable profile of the environment. Barnard's star is extremely dim, emitting only a fraction of the sun's energy. Consequently, despite being relatively close to the star, the planetary companion receives roughly 50 times less solar flux than the Earth receives from the Sunday. This lack of radiant energy suggests that the surface environment is hostile and frozen. Models predict a surface temperature of approximately 105 degrees Kelvin, which translates to 168 degrees Celsius below zero. At these temperatures, any water on the surface would be frozen as hard as granite, and the atmosphere might freeze out onto the ground. However, surface conditions do not tell the entire story. It cannot be ruled out that internal mechanisms act as a secondary heat source. Two primary forces could be at work: the decay of radioactive isotopes within the planet's rocky mantle, and, more significantly, tidal heating caused by gravitational interactions with the star. If these forces are sufficient, they could maintain a layer of liquid water beneath a thick crust of ice. If such a warm subsurface ocean exists, it would be shielded from radiation and stable over billions of years, providing ample time for chemistry to evolve into biology. Time is the one resource Barnard's star possesses in abundance. Among the stellar population in our neighborhood, it appears to be one of the ancient ones. Estimates place its age at over 10 billion years, more than twice the current age of our solar system. This vast timescale implies that any potential biosphere would have had an incredibly long period to adapt and develop because of its proximity, its age, and its motion toward us. Barnard's star remains one of the highest priority targets for theoretical interstellar missions. Whether humanity will ever bridge the gap to visit this freezing, ancient world is a question that only future technological development can answer. Turning our gaze from the dimmest neighbors, we look to the opposite side of the sky relative to the Sunday. Here, we find a star that is the antithesis of the faint red dwarf. This is Sirius, the brightest star in Earth's night sky, located just 8.6 light-years away. To the naked eye, Sirius appears as a single, dazzling point of blue-white light. However, telescopic inspection reveals that this is an illusion. Sirius is not a solitary object. It is a binary system composed of two stars with vastly different histories. Currently, the two components of the system are near their maximum separation from one another, positioned about 30 astronomical units apart, roughly the distance between the Sun and the planet Neptune. The dominant source of light is the main component, designated Sirius A. It is a main sequence star of spectral type A, shining with a brilliant blue-white hue. Physically, it is a powerhouse. It possesses a mass 2 times that of the Sun, and a diameter approximately 70% larger. Its surface temperature is scorching, measured at roughly 10,000 degrees Kelvin. Due to this high temperature and larger surface area, Sirius A emits 25 times more total energy than our Sunday. Orbiting this brilliant beacon is a second object, known as Sirius B. It is barely visible against the overwhelming glare of its massive companion, requiring excellent optics to resolve. Sirius B is a white dwarf, the dead core of a star that has already ended its life. It packs a mass almost equal to that of the Sun into a volume with a radius of only about 6,000 kilometers, making it smaller than Earth. This extreme compression results in high residual heat. Like most young white dwarfs, its surface temperature is intense, reaching 25,000 degrees Kelvin. Yet, because its surface area is so small, it cannot emit much total light. It is approximately 1,000 times dimmer than Sirius A. Astronomers have conducted long and persistent searches for planets within the Sirius system, but no signs of orbiting worlds have been found. The absence of planets may be due to the specific history of this binary pair. One hypothesis suggests that Sirius B was once the more massive of the two stars. Roughly 120 million years ago, it exhausted its hydrogen fuel and expanded into a red giant. During this phase, it would have destabilized the system. Eventually, it shed its outer layers in a violent ejection of mass before shrinking into the white dwarf we see today. This cataclysmic transformation would have had devastating consequences for any protoplanetary disk or existing planets. The explosion likely destroyed the gas and dust reservoirs or scattered the remnants into deep space, effectively sterilizing the system. Currently, the two stars orbit their common center of mass in moderately elongated paths, completing one cycle every 50 years. The dynamics of the system relative to our solar system are also changing. Over the next 60,000 years, the proper motion of Sirius will bring it gradually closer to Earth. It will become even brighter in our night sky until it reaches a minimum distance of about 7.5 light-years. After that closest approach, the system will slowly drift away into the galaxy. The current state of the system is temporary. In approximately 660 million years, Sirius A will deplete its own hydrogen supply. It will follow the path of its companion, swelling into a red giant and then shedding its layers. For a brief astronomical moment, the dying flare of Sirius A will boost its luminosity by a factor of thousands, potentially outshining everything else in the galaxy. from Earth's perspective. But this will be short-lived. Within a few months, the star will fade, collapsing into a white dwarf. The Sirius system will then consist of 2 dead stars, slowly cooling in the darkness forever, leaving the high-energy environment of Sirius, permeated by lethal ultraviolet radiation and stellar winds. We adjust our trajectory to visit a much quieter region. We maneuver back near the solar system to approach a small star located 14 light-years from Earth. It is listed in various catalogs under different designations, but it is most commonly known as Wolf 1061. This star is a classic red dwarf, significantly smaller and cooler than the Sunday. Its radius is roughly 30% of the solar radius, and its mass is about 4 times smaller than that of our star. The surface temperature is a modest 3,272 degrees Kelvin, or about 3,000 degrees Celsius. Like all objects in this class, Wolf 1061 is extremely dim. Its total luminosity is only 0.14% of the Sun's output. Consequently, despite its relative proximity, it is completely invisible to the naked eye from Earth. However, what this system lacks in brightness, it makes up for in complexity. Wolf 1061 hosts one of the most abundant and diverse planetary systems in the solar neighborhood. Precision measurements have confirmed the existence of as many as 3 exoplanets orbiting this small star. All of them are rocky worlds, similar in basic composition to Earth, yet the conditions on each celestial body differ considerably due to their varying distances from the heat source. The first and innermost planet is designated Wolf 1061b. It orbits at a remarkably close distance of just 0.038 astronomical units from the center of the system. To put this in perspective, this is 10 times closer than Mercury is to the Sunday. The planet moves rapidly, completing a full orbit roughly every 5 Earth days. With a mass estimated between 1.5 and 2 Earth masses and a radius 20% larger than our planet, it is a dense, rocky world. However, proximity comes at a cost. It is highly probable that this celestial body is tidally locked. This means the same side of the planet always faces the star, just as one side of the moon always faces Earth. One hemisphere is baked in perpetual daylight, while the other is frozen in eternal night. The temperature on the day side is scorching, and the planet is subjected to intense flares and stellar winds from the red dwarf. These conditions likely stripped away any atmosphere eons ago, ruling out any chance for the genesis or support of life as we know it. Moving outward, we encounter the second object in the system, Wolf 1061c. This planet is located 0.089 astronomical units from the star and completes an orbit roughly every 18 days. This specific distance places it squarely within the star's habitable zone, the narrow belt where temperatures could theoretically allow liquid water to exist on the surface. This status makes it a potentially habitable celestial body. Wolf 1061c belongs to the class of super-Earths, with a mass approximately 3 to 4 times that of our planet. Observations suggest its physical radius is about 1.6 times that of Earth. This increased size implies strong surface gravity, calculated to be 60% higher than what humans experience. While it is in the habitable zone, the planet receives noticeably less total energy from its star than Earth does from the Sunday. The equilibrium temperature is calculated to be 223 degrees Kelvin, or about 50 degrees Celsius below zero. This baseline temperature is slightly warmer than Mars, but still freezing. Nevertheless, the actual surface conditions depend heavily on the atmosphere. If the planet possesses a dense atmosphere capable of generating a pronounced greenhouse effect, it could trap enough heat to raise temperatures significantly. Under those conditions, liquid water could exist, and the environment could approach a state favorable for life. Of all the potentially habitable exoplanets discovered to date, Wolf 1061c ranks as the fifth closest to Earth, making it a prime candidate for future atmospheric study. The third and outermost object in the system is Wolf 1061d. This planet follows a highly unusual path, unlike the near-circular orbits of the inner planets. This world travels on a clearly elongated, eccentric orbit. The distance between the planet and the star varies dramatically. At its farthest point, known as the apastron, the planet swings out into the frozen outer reaches of the system. Conversely, at its closest approach, or periastron, it dives much closer to the internal heat of the star. It takes this celestial object approximately 217 Earth days to complete one full revolution. This constant shift in distance creates a wild fluctuation in climate. As the planet moves from the outer darkness toward the star, it would experience brief, intense summers followed by long, deep winters. This instability makes the surface environment chaotic, challenging the stability required for biological systems to thrive. As we analyze these three worlds, we see a microcosm of planetary diversity: a scorched rock, a potential harbor for life, and a frozen wanderer, all circling a small, dim red star. Yet, our journey through the stellar neighborhood is far from over. We must now look toward a system that has captured the imagination of humanity for centuries, not for its planets, but for its proximity and its iconic status in science fiction. The physical nature of the third planet, Wolf 1061d, remains a subject of calculation and debate. Based on its gravitational influence on the host star, the mass of this object is calculated to be roughly 7.7 times that of Earth. This mass places it in a transitional category where its composition is not immediately obvious. It could be a massive rocky world, or it could be a gaseous dwarf. If this celestial body turns out to be a rocky object composed primarily of silicates and iron, its high density would imply a radius measuring about 1.7 times that of Earth. However, if the planet has retained a significant envelope of hydrogen and helium, it would fall into the category of mini-Neptunes. In this scenario, it would possess a thick, multi-layered atmosphere shrouding a smaller core. Consequently, its diameter would be significantly larger, calculated to be not less than 2.2 times that of our planet. Regardless of its composition, the orbital dynamics paint a bleak picture for habitability. Despite the planet's elliptical path, calculations confirm that Wolf 1061d never enters the star's habitable zone. It remains perpetually frozen in the outer darkness of the system. While likely completely unsuitable for supporting life as we know it, this system poses a great scientific interest in terms of planetary evolution. It serves as a laboratory for understanding how multiple planets can form and survive in compact orbits around small red dwarf stars. Because of this complexity, this system remains one of the top priority destinations for future telescopic exploration. It is highly probable that as our instruments improve, new discoveries regarding the atmospheric composition of these worlds will be made. Leaving the specific gravity of the Wolf system, we must now consider the medium through which we are traveling. The star, Wolf 1061, is remarkable not just for its planets, but for its location. It sits virtually at the very edge of a massive galactic structure known as the local interstellar cloud. Contrary to the popular belief that space is a perfect vacuum, The voids between stars are filled with matter, albeit in extremely low concentrations. This specific cloud is a region of space spanning roughly 30 light-years across, filled with hydrogen and helium gas. The physics of this cloud are counterintuitive. The gas within it is technically hot, with a kinetic temperature measuring about 7,000 degrees Kelvin. This is hotter than the surface of the Sunday. However, a human spaceship traveling through it would not melt. The heat is contained in the high speed of the individual atoms, but the density is so incredibly low that there is almost no transfer of heat energy. On average, there is just 0.3 atoms to be found in every cubic centimeter of space. To visualize this, it is a vacuum far more perfect than any laboratory on Earth can create. Yet, it is about twice as dense as the average value in the wider Milky Way galaxy. Our solar system is not a permanent resident of this structure. We have been moving through the local interstellar cloud for approximately the past 10,000 to 40,000 years. Currently, our Sun is located near the edge of this cloud. Other nearby systems, like Alpha Centauri, reside in a neighboring structure called the G-cloud. Based on our current velocity and trajectory, humanity's solar system will remain within this local mist for another 2,000 years. After that, we will exit this structure and enter an even thinner, hotter region of the interstellar medium, often referred to as the local bubble. The origin of the local interstellar cloud is violent. It was formed by the collision of two giant bubbles of hot cosmic gas, likely expanded by ancient supernova explosions. This collision compressed the gas into the filament we see today. The cloud is not static. It has a momentum of its own, moving perpendicular to the direction of the solar system's motion. It also possesses a weak magnetic field and is permeated by cosmic radiation. Fortunately for life on Earth, despite the high energy of the interstellar gas particles that make up the cloud, there is no direct threat to organisms on our planet. The Sun generates its own protective bubble, called the heliosphere, a vast region dominated by the solar wind. This stream of charged particles from the Sun pushes against the interstellar medium, acting as a reliable shield against cosmic hydrogen. For the particles that do manage to break through the heliosphere, Earth's dense atmosphere serves as the final barrier, absorbing the impact. However, physical evidence of our journey through this cloud exists. Traces of a specific radioactive isotope, Iron-60, also known as interstellar iron, have been found in deep-sea crusts and in the pristine ice of Antarctica. Since Iron-60 decays relatively quickly and is not produced naturally on Earth, its presence suggests it arrived recently from deep space. It is thought to be dust from ancient supernovae that was trapped in the local interstellar cloud and then deposited on Earth as we traveled through it. As we continue our journey through this diffuse medium, we adjust our coordinates to intercept a rather unusual object. Located 27.4 light-years away from Earth is the star designated AP Columbae. At first glance, it appears to be a standard red dwarf, but closer inspection reveals it is a cosmic anomaly. First and foremost, it draws our attention because of its extreme youth. AP Columbae was born just 40 million years ago. To put that in perspective, this star ignited long after the dinosaurs had died out on Earth, and mammals had already begun to dominate the planet. What is even more striking is its location. Stars are typically born in clusters and drift apart slowly. However, the birth of AP Columbae took place in a completely different region of the galaxy, roughly 450 light-years away from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. The fact that AP Columbae is here in our neighborhood implies a violent history. If you analyze the movement vector of AP Columbae and trace it backward in time, you will find that it likely originated from the open star cluster, designated IC 2391, also known as the Omicron Velorum cluster. This cluster contains about 30 stars united by a common origin and direction of movement. The leading hypothesis suggests that a few million years ago, a massive star within that cluster exploded as a supernova. The shockwave from this catastrophe shattered the delicate gravitational equilibrium of the group. This event gave the young AP Columbae a massive kick, additional momentum that swiftly expelled it from its birthplace and sent it shooting across the galaxy to arrive near us. Physically, AP Columbae is a pre-main sequence red dwarf. It has a mass of just 13%, that of the Sunday. However, because it is still gravitationally contracting and has not yet fully settled, it is unusually energetic. It emits 4 times more energy than any other known celestial body with the same mass parameters. In addition, its physical size reflects its immaturity. Its radius is twice as large as calculated for a mature star of its mass. It is effectively a bloated infant star. Confirmation of its youth comes from chemistry. Spectral analysis of its radiation reveals that the stellar matter of AP Columbae contains an abnormally large amount of lithium. In stellar physics, lithium is known as the cosmic clock. Normally, this element is found in abundance in protostellar clouds. However, lithium nuclei are fragile. They burn out and are destroyed almost immediately once a star initiates sustained thermonuclear fusion. The fact that AP Columbae is still rich in lithium confirms that it is very young and at the very beginning of its formation. It has not even fully entered the main sequence phase yet. As a consequence of this youth, AP Columbae is highly unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, superflares that dwarf anything produced by our Sunday. During these events, its luminosity may increase by up to 10 times for a short while. Such violent magnetic activity creates a hostile environment. These events would normally threaten any exoplanets nearby, stripping off their atmospheres and sterilizing their surfaces with intense ultraviolet and X-ray radiation. Current observations confirm this barren state. There are no large space objects detected within 4.5 astronomical units of this star. In all likelihood, the system is too young and chaotic for the formation of fully fledged planets to have completed. Nevertheless, AP Columbae remains a unique cosmic body for astronomers. It provides a rare opportunity to study the early evolutionary stages of red dwarfs up close, effectively allowing us to look back in time at how common stars behave in their infancy. Leaving this volatile young runaway, we set our course for a more mature and potentially stable system. Our next stop is near the orange dwarf star designated Gliese 370, located roughly 36 light-years from Earth. This star is slightly larger and brighter than the red dwarfs we have visited previously. In the year 2011, astronomers using the radial velocity method detected a signal embedded in the star's light. This signal confirmed the presence of a single exoplanet, designated Gliese 370b, or widely known in catalogues as HD 85512b. The mass of this object is estimated to be roughly 3 to 4 times that of Earth, placing it in the category of super-Earths. According to current models of celestial body formation, a planet of this mass is most likely rocky in composition, similar to Earth, but scaled up. Its physical radius is estimated to be about 30% larger than Earth's radius. This increase in size and mass has direct consequences for gravity. An explorer standing on its surface would experience a gravitational pull at least 40% stronger than what we are used to on our home planet. The orbit of Gliese 370b is significantly closer to its star than Earth is to the Sunday. It is located at a distance of 0.26 astronomical units, roughly a quarter of the distance from Earth to the Sunday. It completes an annual rotation, or 1 full year, in just 54.4 Earth days. Despite this proximity, because the parent star is cooler and dimmer than the Sun, this orbit places the exoplanet within the inner edge of the habitable zone. This is the region where temperatures could theoretically allow liquid water to exist. Assuming the planet has an albedo or surface reflectivity similar to that of Earth, models suggest the equilibrium temperature of the celestial body should be about 25 degrees Celsius. This is a few degrees higher than the average on Earth, implying a warm, tropical environment. Crucially, the fact that the exoplanet is located at this specific distance suggests that it is likely not tidally locked. It should possess its own day-night cycle as it rotates on its axis. This rotation contributes to an even distribution of heat over the surface, preventing the atmosphere from freezing on a dark side or boiling on a day side. Consequently, this heat distribution may create a mild, stable climate. The moderately high surface gravity would likely smooth out the planet's terrain, reducing the height of mountains and depth of valleys. This geology, combined with the potential abundance of liquid water, has led scientists to hypothesize the existence of vast, shallow seas covering much of the surface. Such warm, stable marine environments have traditionally been considered the most comfortable incubators for the genesis and support of biological life. At the time of its discovery, Gliese 370b was hailed as one of the most favorable candidates for extraterrestrial habitability. However, science is a process of refinement, and more recent research has suggested that conditions on its surface might be more extreme than previously thought. The proximity to the star puts the planet at risk of a runaway greenhouse effect. If the atmosphere of the celestial body is too dense, it would trap heat too efficiently. Instead of a tropical paradise, the surface could resemble a steam bath. Still, even according to the most pessimistic thermodynamic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius. This corresponds to a temperature range of about 30 to 100 degrees Celsius. While this sounds extreme to modern humans, it is important to remember our own history. Geologic evidence suggests that Earth's climate was very similar to this hot, steamy, and ocean-dominated during the Archean Eon, billions of years ago. It was in exactly these conditions that single-celled life first thrived on our planet. Therefore, Gliese 370b remains a very promising target. It represents a version of Earth as it might have been in its deep past. This means that its exploration must continue, as it holds clues not just to alien life, but to the origins of life itself. If we pause our journey to assess our position relative to Earth, we find that we have already traveled more than 50 light-years from the solar system. We have moved beyond the immediate neighborhood of the Sunday. A survey of a sphere with this radius reveals a densely populated region containing over 1,000 individual stars. The majority of these are solitary travelers, much like our own Sunday. However, a significant percentage exists in more complex arrangements, binary systems, where two stars orbit a common center, or even higher-order multiple systems. Among these, the most striking example of stellar complexity is the system designated Alpha Geminorum, historically known to humanity as Castor, located approximately 51 light-years away from Earth. Castor presents itself to the naked eye as a single, brilliant point of light. It serves as the second brightest object in the constellation Gemini, the twins, and ranks as the 23rd brightest star in the entire night sky. Because of its prominence, it has been a navigational guide and a mythological symbol since ancient civilizations first charted the heavens. However, the singular appearance of Castor is a grand illusion maintained by distance. Telescopic analysis reveals that this is not one star, but a chaotic gravitational dance of 6 individual components. It is a sextuple system. The architecture of Castor is hierarchical. The system is dominated by 2 bright central pairs, designated Castor A and Castor B. These 2 primary components are bluish-white stars, similar in spectral type to Sirius. They are main sequence stars, hotter and more massive than the Sun, radiating with intense energy. Yet, neither Castor A nor Castor B is alone. Detailed spectroscopic analysis, observing the Doppler shift in their light, reveals that each of these white giants is orbited by a smaller, fainter companion. These companions are red dwarfs, invisible to the optical telescope, but betraying their presence through gravity. The distance between the centers of mass of the Castor A pair and the Castor B pair is approximately 110 astronomical units, roughly 3 times the distance from the Sun to Pluto. Bound by gravity, these 2 binary systems perform a slow, majestic orbit around one another, taking approximately 445 years to complete a full revolution. But the complexity does not end there. Orbiting at a vast distance from this central quadruple waltz is a 3rd component, known as Castor C, or by its variable star designation, YY Geminorum. Located about 1,000 astronomical units away from the central pairs, Castor C is physically disconnected from the bright inner region. It consists of a pair of almost identical red dwarfs. These 2 small stars are locked in an extremely tight embrace. Their mutual orbit is so compact that they complete a full rotation around each other in less than 20 hours. Because their orbital plane is aligned with our line of sight from Earth, these 2 red dwarfs eclipse each other with every revolution, causing the light from the pair to dip rhythmically. While the inner pairs take centuries to orbit, the Castor C pair races through space, taking roughly 14,000 years to complete one giant circuit around the primary Castor A and B systems. To date, astronomers have not confirmed the presence of any stable planetary bodies within the chaotic gravity wells of the Castor system. However, if planets do exist, dynamic models suggest they would most likely be found orbiting the fainter, distant component, Castor C. In 2018, researchers detected subtle variations in the orbital timing of the Castor C pair. This perturbation implies the presence of a substellar companion, likely a brown dwarf. Calculations suggest this hidden object possesses a mass roughly 49 times that of Jupiter. It is theorized to orbit at a distance of 14 astronomical units from the red dwarf pair, completing a cycle every 54 years. It is entirely possible that, like many red dwarf systems, Castor C could host rocky exoplanets in stable orbits. If we were to stand on the surface of such a hypothetical world, the skyline would present a truly incredible spectacle, unlike anything seen on Earth. On one side of the sky, the view would be dominated by the 2 primary crimson suns, Castor C1 and C2, circling each other rapidly, causing shadows to shift and lengthen hour by hour. On the other side of the sky, looking toward the distant center of the system, the observer would see two brilliant points of light, Castor A and Castor B. Though distant, they would shine hundreds of times brighter than the full moon seen from Earth, casting a permanent, eerie twilight that banishes true darkness from the night. Whether this dramatic landscape actually exists remains a question for future verification. Although the stars we have visited from Barnard's Star to Wolf 1061 and Castor are separated by great distances, they all reside within a single, colossal structure of the interstellar medium. This structure spans a total diameter of approximately 300 light-years and is known as the local bubble. This bubble is effectively a cavity in the galaxy's disk. It contains not only thousands of stars but also several independent interstellar clouds, including the local interstellar cloud we discussed earlier. The origins of the local bubble trace back to a violent epoch between 10 and 15 million years ago. During this period, a cluster of massive stars in the solar neighborhood reached the end of their lives. They detonated as supernovae in a rapid sequence. The shockwaves from these multiple explosions acted like cosmic snowplows, sweeping up the dense, cold gas and dust of the interstellar medium and pushing it outward. This created a shell of dense material on the perimeter and left behind a hollow interior. Inside this cavity, the gas is incredibly hot, heated by the energy of the explosions to temperatures approaching 1 million degrees Kelvin. However, this leads to a paradox. While the temperature is high, the density is remarkably low, about 10 times lower than the average density of the Milky Way. Because the atoms are so sparse, they cannot transfer this heat effectively to solid objects. This hot, ionized hydrogen plasma constantly emits energy in the X-ray spectrum, contributing to the diffuse X-ray background detected by space telescopes. Fortunately for life, the magnetic fields of the Sun and the Earth, as well as the planet's thick atmosphere, successfully act as shields, protecting the biosphere from this pervasive ionizing radiation. The local bubble is not an isolated feature. It is bordered by other similar formations, creating a structure often compared to Swiss cheese. For example, slightly away from the direction of the solar system's motion lies the Loop 1 bubble. This neighboring cavity was formed by supernova explosions in the Scorpius-Centaurus association, specifically in the vicinity of the supergiant star Antares. This giant cosmic structure has been actively interacting with our own local bubble for millions of years. The collision zone between these two expanding bubbles has caused the formation of a wall of dense neutral gas. The center of this neighboring bubble lies about 500 light-years from us. Based on current trajectories, the solar system is drifting through the local bubble and will reach its outer margins in a few tens of millions of years. Extending our journey significantly further, we travel 650 light-years away from Earth to encounter a star in the final, dramatic stages of its existence. This object is designated IRC +10216, but it is more commonly known to astronomers as CW Leonis. It is a red giant, specifically a carbon star, and it is a monster. CW Leonis is a pulsating variable star. Its size is not fixed. It breathes. At the peak of its pulsation cycle, the radius of this star expands to reach 560 times the radius of the Sunday. To visualize this scale, imagine placing CW Leonis in the center of our own solar system. The surface of the star would extend out past the orbit of Earth, past the orbit of Mars, and would brush against the inner boundary of the main asteroid belt. Every planet from Mercury to Mars would be engulfed and incinerated instantly. Incidentally, despite this colossal volume, the star's mass is not excessively large. Estimates place it between 1.5 and 4 times the mass of the Sunday. Its surface temperature is relatively cool for a star, measuring just 2,300 Kelvin, or about 2,000 degrees Celsius. This low temperature gives it a deep, reddish-orange color. However, due to its impressive surface area, the star functions like a massive radiator, emitting on average 8,500 times more total energy than our Sunday. Like any other red giant, CW Leonis is in the final chapter of its life cycle. Its exact age has not been defined precisely, but it is estimated to be several billion years old. We can reconstruct its history using stellar evolution models. It is assumed that in its early epoch, its main sequence phase, CW Leonis, was a blue-white star, perhaps 3 to 5 times more massive than the Sunday. It burned brightly and hot. However, by about 1 billion years ago, the hydrogen fuel in its core was exhausted. As the hydrogen fused into helium, the ash of the reaction settled in the star's center. Eventually, the core became composed entirely of inactive helium. Without the outward pressure of fusion to support it, the core collapsed under gravity, while the hydrogen burning moved to a shell surrounding the core. This structural change forced the outer layers of the star to expand outward, cooling as they grew. This is the standard transition into a red giant. However, deep inside, the conditions became critical. As the helium core continued to shrink, its density increased until the electrons were packed so tightly that they became degenerate. In this state, the core pressure no longer depends on temperature. When the temperature finally rose high enough to ignite helium fusion, the core could not expand to regulate the heat. The result was a runaway thermonuclear event known as the helium flash. In a matter of seconds, the core released an amount of energy comparable to the output of an entire galaxy. This energy was absorbed by the star's outer layers, triggering a structural reconfiguration. The helium nuclei began fusing into carbon and oxygen. This brings us to the current state of CW Leonis. It has evolved onto the asymptotic giant branch. The star is now a factory for heavy elements. Deep convection currents, movements of plasma similar to boiling water, act as a dredge. They reach down into the burning interior and pull the newly created carbon up to the surface. This dredge-up process has enriched the outer atmosphere with carbon, far exceeding the amount of oxygen. This is why CW Leonis is classified as a carbon star. Currently, the star holds great amounts of carbon, but its mass is not sufficient to generate the pressure needed to fuse carbon into heavier elements like neon or magnesium. It has hit a dead end in terms of nucleosynthesis. Because the surface is rich in carbon and relatively cool, the carbon atoms bond to form complex molecules, including silicon carbide and graphite, essentially soot. The stellar wind blows this carbon dust out into space, creating a dense, dark cocoon around the star. This dust shell absorbs almost all the visible light from the star and re-radiates it as infrared energy. In fact, CW Leonis is the brightest object in the entire sky outside the solar system when viewed at certain infrared wavelengths. The ultimate fate of CW Leonis is already sealed. The pulsations we observe today will grow more violent. With each expansion, the star pushes its outer layers further away, where the gravity is too weak to hold them back. In a few tens of thousands of years, a blink of an eye in cosmic time, the entire outer envelope will be ejected. The carbon-rich dust and gas will form a spectacular planetary nebula, glowing with the light of the exposed, hot core. That core will then cool down to become a white dwarf, a diamond in the sky composed of carbon and oxygen, slowly fading into eternity. Leaving the dusty shroud of the carbon giant, we must now prepare for an encounter with the most destructive force in the universe. Our journey takes us next to a celestial body that has already completed this transformation, but with a mass so great that even the white dwarf stage could not halt its collapse. We approach the realm of the black hole. Here, we will witness how extremely strong gravity distorts and tears apart the very fabric of the universe, giving rise to amazing natural phenomena. In the deep interior of CW Leonis, the stability that defined the star for billions of years has completely broken down. The thermonuclear combustion of helium into carbon is no longer a smooth, continuous process. Instead, it has become erratic and unstable, driven by a vicious cycle of pressure and gravity. It begins when the nuclear fuel in the burning shell is temporarily exhausted. Without the outward pressure generated by fusion energy, the star can no longer support its own immense weight. Consequently, the stellar matter gradually cools off and begins to shrink under the heavy hand of gravitation. As the layers collapse inward, the compression causes the internal temperature to spike dramatically. This sudden injection of heat reignites the dormant helium shell. The reaction is unleashed with a renewed, explosive force, generating a massive pulse of thermal energy. Upon receiving this new portion of energy, the stellar matter expands violently outward again. As it expands, it cools, the density drops, and the combustion dies down once more, resetting the cycle. It is assumed by astrophysicists that this cyclic process, technically known as a thermal pulse, underlies the dramatic changes observed in the star's luminosity. CW Leonis is not shining steadily, it is throbbing. Observations indicate it has a pulsation cycle of approximately 649 days. The variance in brightness is staggering. When the luminosity is at its peak, this giant shines with an intensity 11,300 times brighter than the Sunday. Even when the luminosity falls to its lowest point during the expansion phase, the object still emits 6,250 times more energy than our home star. This violent breathing of the star has physical consequences. At the moment of contraction, when the star shudders, the upper layers of the stellar atmosphere act like a piston. They detach themselves from the star's gravitational hold and are cast off into deep space. This ejected material cools and condenses, forming the vast carbon-oxygen gas nebula that envelops the star. The rate at which CW Leonis is evaporating is difficult to comprehend. According to some estimates, this star loses approximately 4 times 10 to the power of 22 tons of material every single year. To visualize this, imagine taking the entire mass of the Earth, crushing it into dust, and blowing it into space. CW Leonis does this 7 times every year. Over millennia, this creates a massive shroud. Observations show that the circumstellar nebula surrounding the star is not less than 69,000 years old. The total mass of this ejected cloud is immense, calculated to be about 1.5 times the mass of the Sunday. As for its physical extent, the nebula reaches out to a radius of 84,000 astronomical units. This is far larger than our entire solar system. It extends into the interstellar medium, creating a bubble of dust that blocks visible light. Recent high-resolution imaging reveals that this nebula is not a simple sphere. It possesses an elaborate asymmetric structure featuring complex bulges, density pockets, as well as clearly defined half-arcs and irregular rings. It is posited that these specific formations are not random. They likely appear due to the complex interplay between the star's erratic magnetic activity and the stellar wind. However, the archery target pattern of rings strongly suggests the presence of a gravitational influence from a secondary object nearby. Beyond its structure, the chemical composition of the cloud CW Leonis is of great interest to explorers. It is effectively a cosmic chemical factory. Spectral analysis data reveals the cloud to contain around 70 different chemical compounds. Simple molecules like carbon dioxide, water, and ammonia are present, but so are complex organic chains. Most notably, the cloud is rich in elements from the upper part of Mendeleev's periodic table. Instruments have detected traces of heavy metals right down to iron, which have been dredged up from the core and spewed into the void. The question of what orbits this dying giant remains open. CW Leonis may have had a retinue of planets in the past, similar to our solar system. However, if they existed in the inner regions, they appear to have been swallowed up early on during the red giant expansion phase. In any event, years of observations have not revealed distinct traces of their existence. What was registered, however, were subtle gravitational clues. Back in 1994, astronomers detected minute changes in the star's proper motion, a wobble that suggested it was being tugged by an unseen partner. More recently, in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. The spiral patterns observed in the dust are characteristic of a binary interaction. Some small red dwarf orbiting the giant could well account for these phenomena. Although attempts to visually detect its radiation have so far been unsuccessful, this is likely not because the star isn't there, but because it is hidden. The nebula close by is so thick that it disperses and reflects the energy flow from sources of light located nearby. This phenomenon, known as scattering, camouflages any objects in the immediate environment and prevents them from being accurately recognized by our telescopes. Based on the dynamics of the dust, the mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sunday. Calculations suggest it takes approximately 100 years for this hidden partner to complete a full orbit around the giant. One of the most perplexing mysteries of CW Leonis is the presence of water. Another outstanding feature of this system is a comparatively high water content in the star's environs and envelope. In the context of a carbon star, this shouldn't be possible. In stellar chemistry, carbon atoms usually bond with all available oxygen atoms to form carbon monoxide, Co, a very stable molecule. Only the leftover oxygen should be available to form water, H2O. Since CW Leonis is a carbon star, it has more carbon than oxygen, so all oxygen should be locked up in CO, leaving none to make water. At first, researchers posited that the star might be melting and swallowing a vast reservoir of icy comets, the remnants of its destroyed solar system, as it expanded. However, observations carried out in 2009 by the Herschel Space Observatory disproved this. The data showed the temperature of some spectral lines of water to reach 1000 degrees Kelvin. This temperature is far too hot for the outer comet cloud. It is possible only on the condition that water vapor forms actually in the upper layers of the giant itself. This fact did not fit in the model of red giant structure accepted at the time. A new hypothesis was put forward to account for the witnessed phenomena. It stated that molecules of silicon oxides and carbon monoxide are being destroyed by a source of powerful ultraviolet radiation. This radiation breaks the chemical bonds, freeing the oxygen. After that, the liberated oxygen reacts with the abundant hydrogen in the stellar wind, and there forms scorching hot water vapor. The weakness of this hypothesis lies in the failure to account for the source of the ultraviolet radiation. Red giants are cool stars. They emit very little UV light. Reactions like that may occur only in rather high temperatures that exist within the deep stellar matter or from a hot companion. However, the deep interior is practically impervious to cosmic rays or external light. This paradox may be explained by yet another assumption regarding the star's physical structure. Since the star is unstable, it is not a smooth sphere. Large ruptures and low-density areas, often called holes in the photosphere, occasionally occur on its surface. Through these gaps, the intense ultraviolet radiation from the hot interior or the chromosphere can escape outward. In these specific zones, the UV radiation is not blocked out effectively, allowing it to hit the gas shell and manufacture water. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons, a mass several thousand times that of Earth's oceans. Enormous though this figure may seem, in fact, given the scale of the star, water accounts for just around 1/1000th of the star's overall mass. It is a trace contaminant, but a scientifically crucial one. According to today's notions of stellar evolution, C.W. Leonis has reached the end of the line. Being a red giant on the asymptotic giant branch, it is in its autumn years now. The fuel is running out. Calculations predict it will deplete its remaining stellar fuel in the next 10,000 to 30,000 years. This is a blink of an eye in geological time. Once the fuel is gone, the radiation pressure that holds the outer layers up will vanish. However, the core will remain hot. It will discard its outer layers following a final, powerful ejection event, creating a glowing planetary nebula. The core will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, but compressed into the volume of the Earth. Its temperature will be staggering, reaching several million degrees in the first seconds after the transformation. However, unlike a main sequence star, a white dwarf has no internal engine. Fusion has stopped. With no energy source to replenish the heat, it is destined to slowly and irrevocably fade. It will radiate its stored thermal energy into the vacuum in the course of billions of years to follow. It will turn from blue-white to yellow, then to red. Eventually, the celestial body will cool until it emits no visible light, becoming almost invisible against the background of cosmic emptiness. It will become a mysterious black dwarf, a cold, dark cinder floating in the void. But this will not happen anytime soon. The universe is currently about 13.8 billion years old, which is not enough time for a white dwarf to cool down completely. No black dwarfs exist yet. Before it fades, the death of this star leaves a vital legacy. The shock wave and the mind-boggling temperature in the epicenter of the final helium flashes generate a unique environment for nuclear physics. These conditions allow for the S process, or slow neutron capture process. This mechanism generates new heavy elements that are not to be found in a normal star's interior. For example, valuable and heavy isotopes like uranium, gold, and lead are forged in these dying moments. These elements are then blown out into the galaxy within the nebula. They will mix with the interstellar clouds and later become part of new celestial objects. Billions of years later, when a new solar system forms from this dust, these elements will play a crucial role. The radioactive decay of elements like uranium and thorium, created in stars like CW Leonis, will provide internal heat for rocky planets. This heat will melt the planet's interiors, drive plate tectonics, and prevent the core from freezing. It will melt the ice and saturate the oceans with microelements. Thus, the death of one star creates the chemical and geothermal conditions necessary for the genesis of life on a world that does not yet exist. The evolution of the cosmos is a continuous cycle of construction and annihilation. Global cataclysms are not anomalies. They are an inalienable part of the process that shapes the galaxy. Yet, astrophysical theory suggests that even in the aftermath of the most violent destruction, stable structures can emerge. We now turn our attention to the endpoint of high-mass stellar evolution, the black hole, detecting an object that, by definition, absorbs all electromagnetic radiation incident upon it, is a challenge that pushes the limits of modern astronomy. Because they emit no light of their own, black holes are invisible against the black backdrop of space. Consequently, the number of confirmed black hole candidates remains relatively small. However, we must not mistake a lack of detection for a lack of existence. Advanced mathematical modeling of stellar populations suggests that our Milky Way galaxy is teeming with them. Estimates indicate that the number of stellar mass black holes in our galaxy alone may reach 100 million. While this figure appears staggering, it must be viewed in context. The Milky Way contains between 200 billion and 400 billion stars. Therefore, statistically speaking, for every few thousand shining stars, there is only one black hole hiding in the dark. In the vast expanses of interstellar space, they remain rare, isolated objects that a traveler would be unlikely to encounter by chance. To understand where they come from, we must look back at the progenitors. As discussed in previous analyses of stellar life cycles, not every star earns this dark fate. The progenitor star must possess a mass of at least 18 to 20 times that of the Sunday. Only a star of this immense caliber can generate the gravitational pressure required. When such a star dies, the resulting supernova explosion crushes the core with force sufficient to overcome neutron degeneracy pressure. The scorching hot core is compressed into an exceptionally dense clump of material. Once the core collapses below a critical size, known as the Schwarzschild radius, the escape velocity required to leave its surface exceeds the speed of light. At this point, the object effectively disconnects from the rest of the observable universe. Nothing, neither matter nor information, can stand up to the object's gravitational force and escape beyond this invisible sphere. What used to be a star transforms into a singularity, an object with an inner makeup that defies description by the classical physical laws we are familiar with. One of the most compelling examples of such an object lies relatively close to Earth. Designated as a 062-0-00, or alternatively V616 Monocerotis, this system offers a glimpse into the behavior of these dark giants. Located approximately 3,300 light-years away in the constellation Monoceros, the Unicorn, it is not a solitary object, but a binary system. The visible component of this system is an orange dwarf star, spectral type K, with a mass roughly half that of the Sunday. However, its behavior reveals that it is not alone. Observations show that this star is being whipped around a common center of mass at a breakneck speed. It completes a full orbit around an invisible companion every 7.75 hours. By applying Kepler's laws of planetary motion to this orbit, astronomers have weighed the invisible partner. Estimates place the mass of this unseen object at approximately 6.6 times the mass of the Sunday. This is the smoking gun. This mass is too great for a white dwarf and significantly exceeds the theoretical maximum mass limit for a neutron star, which is about 2.2 solar masses. This leaves only one conclusion. The bizarre, invisible object is, in all probability, a stellar mass black hole. The relationship between the two is parasitic. The orange dwarf is close enough to the black hole that it is being deformed into a teardrop shape by intense tidal forces. It is slowly being stripped of its outer layers. Streams of scorching hydrogen gas are pulled from the star's surface. However, due to the conservation of angular momentum, this gas does not fall directly into the black hole. Instead, it spirals inward, forming a flat, rapidly rotating structure known as an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to shine brilliantly in the X-ray spectrum. It is thanks to this dazzling high-energy disk that the black hole was detected at all. The environment around V616 Monocerotis is crowded. There are at least several dozen other stars in the immediate vicinity, some of which almost certainly host their own planetary systems. It is highly likely that in the distant future, the galactic orbit of one of these neighboring stars will bring it dangerously close to the black hole. If it crosses a certain gravitational threshold, it will be captured. The unfortunate star will have no choice but to succumb to the same slow demise as the current orange dwarf companion gradually consumed to feed the accretion disk. The physics of this interaction depends entirely on the mass ratio and distance. As a star approaches a black hole, the differential in gravity, the fact that the pull on the near side is stronger than on the far side, creates tidal forces. These forces stretch the star towards the system's center of mass, a process often referred to scientifically as spaghettification. In binary systems, these forces can open gravitational channels, effectively siphoning matter from the star to the black hole. If the tidal forces are strong enough, they do not just deform the star, they destroy it. A star venturing too close can be ripped apart entirely, turning from a spherical body into a fiery ring of debris in a matter of hours. This is known as a tidal disruption event. However, in contrast to widespread popular opinion, black holes are not cosmic vacuum cleaners that indiscriminately suck in everything around them. From the point of view of classical gravitation, they behave exactly like any other star of the same mass. If our Sun were instantly replaced by a black hole of equal mass, Earth would not get sucked in. It would continue to orbit the black hole in the exact same path, merely freezing in the darkness. Because of this gravitational stability, it is entirely possible for a black hole to host a stable planetary system. There are several theoretical mechanisms by which such a dark solar system could form. The first scenario involves second-generation formation. After the progenitor star explodes as a supernova, a vast nebula of gas and heavy dust remains. Under the influence of the black hole's gravity, this debris can flatten into a protoplanetary disk, distinct from the hot accretion disk. Within this cooler disk, clumps of material collide and merge, attracting cosmic dust. Over millions of years, they could coalesce into planets, moons, asteroids, and comets, just as they do around a normal star. Crucially, the black hole's accretion disk, the ring of superheated gas falling into the hole, can emit tremendous amounts of light and heat. If a planet orbits at the correct distance, this radiation could substitute for sunlight. It could be powerful enough to warm the planet and even melt ice on its surface. Hypothetically, such a Goldilocks zone around a black hole could create conditions favorable for the genesis of life, though the radiation environment would be perilous. The second scenario involves capture and transformation. If a black hole captures an existing solar system, the violence of the event would bring about dramatic changes to the planetary surfaces. For example, a captured gas giant might be subjected to intense stellar winds from the accretion disk. Over time, it could lose almost all of its light hydrogen and helium atmosphere, leaving behind only the dense, rocky, or metallic core. Astronomers call this theoretical remnant a Chthonian planet. Alternatively, an ice giant like Neptune could be melted, transforming into a deep, global ocean planet. The third scenario involves the gravitational entrapment of space wanderers. The galaxy is full of rogue planets, worlds ejected from their home systems, drifting in the void as well as interstellar asteroids. These objects may pass close enough to be ensnared by the massive object's gravity, settling into stable orbits. Even though systems like this have not yet been observed directly, due to the difficulty of detecting small, dark objects around dark, massive ones, the laws of physics provide no reason to suppose they are non-existent. However, orbital stability has its limits. If a planet forms too close to the center, or if its orbit decays, other factors come into play. If a planet enters the region of the accretion disk, the friction from the diffuse gas will act as a drag force. This friction will strip the celestial object of its atmosphere and slow its orbital velocity. As it slows, it spirals inward. Eventually, it reaches the Roche limit, the point where the black hole's tidal gravity exceeds the planet's own self-gravity. At this boundary, the planet ceases to exist as a solid body. Extremely powerful tidal forces will overcome the chemical bonds holding the rock together, ripping the planet to tiny shreds and adding its mass to the growing darkness. As we contemplate these extreme environments, we must also consider the heart of our own galaxy. We are now approaching a region where the density of stars increases dramatically, and the forces at play are scaled up to a level that challenges the imagination. We are heading toward the galactic center. Any debris caught in this gravitational trap faces an inevitable fate. As the material spirals inward, it enters the accretion disk, where friction generates temperatures high enough to melt and vaporize rock and metal instantly. Eventually, this superheated gas crosses the event horizon. Once it passes this boundary, it is swallowed up by the black hole, adding its mass to the singularity and effectively becoming part of it. While all black holes share the same fundamental property, gravity so strong that light cannot escape, they are not all identical. Current astrophysical theory posits that there are three main categories of black holes found in the universe, differentiated primarily by their mass and their origin story. The first and most impressive category consists of the supermassive black holes. These gargantuan objects are not scattered randomly. They are found anchoring the centers of most large galaxies, including our own Milky Way. Their physical scale is difficult to comprehend, with masses reaching millions or even several billion times the mass of the Sunday. The origin of these giants is tied to the evolution of galaxies themselves. In the central region of a galaxy, the density of matter is extremely high. This environment promotes the formation of a large number of massive stars, packed closely together. As these stars rapidly burn through their fuel and die, they transform into black holes. Because of the crowded environment, these black holes feed voraciously on gas and frequently merge with one another. Over billions of years, this process builds a monster. When these supermassive objects are actively feeding, they are surrounded by giant accretion disks made of scorching hot material. This disk converts gravitational energy into light with terrifying efficiency. They illuminate space so brightly that they can be seen from billions of light years away, outshining the entire galaxy that hosts them. Even if the host galaxy is too faint to be observed from Earth, the active nucleus remains visible. These blazing beacons powered by black holes are known as quasars. The second type is the stellar mass black hole. These are much more widespread throughout the galaxy, but at the same time, they are significantly harder to detect because they are smaller and darker. Their masses typically range from roughly 5 to several dozen times the mass of the Sunday. These form directly from the core collapse of massive stars at the end of their life cycles, as we observed with the binary system earlier. By devouring other celestial bodies and stripping gas from the interstellar medium, these objects gradually gain in size. Over time, they may evolve into a transitional category known as intermediate mass black holes. Furthermore, these objects do not always remain solitary. When two black holes orbit each other and eventually merge, the collision is so violent that it shakes the fabric of space-time itself. These collisions generate gravitational waves, ripples in the universe, that can be detected by instruments on Earth even after traveling for many light years. The third type belongs to the realm of the hypothetical, primordial black holes. Unlike the others, these are not born from dead stars. Their existence has been inferred from modern theories regarding the universe's origins. In the fraction of a second after the Big Bang, the universe was not perfectly uniform. There were fluctuations in the density of matter. It is theorized that some regions were so dense that they collapsed directly into black holes. These primordial objects could be infinitely small, with masses comparable to an asteroid or a mountain, but compressed into the size of a proton. An interesting property of black holes is that they are not perfectly stable. They slowly leak energy through a process known as Hawking radiation. According to estimates, the smaller an object of this type is, the faster it evaporates. At the very end of its life cycle, a primordial black hole would destabilize completely, turning its remaining mass into a tremendously powerful electromagnetic impulse. Mathematical modeling suggests that primordial black holes with masses around 10 to the power of 12 kilograms should be reaching the end of their lives right now, appearing as flashes in the sky. But to date, no such event has been registered, leaving their existence unproven. There is also a sub-hypothesis suggesting that a microscopic black hole could form during the collision of extra high-energy elementary particles. This variety is referred to as a quantum black hole. However, the energy levels required to create such an event are astronomical, far beyond anything that can be reproduced in laboratory conditions like the Large Hadron Collider. Furthermore, the estimated life expectancy of these hypothetical objects is so brief that they would evaporate almost instantly. Therefore, quantum black holes currently exist only in theoretical physics. Detecting these dark and compact objects remains one of the most difficult tasks in astronomy. Since we cannot see them directly, we look for their fingerprints on the surrounding universe. As we discussed, some of them happen to have a star companion, the anomalous trajectory of the visible star, gives telltale prompts that it is orbiting an invisible heavy anchor. Another popular method of detection is the observation of accretion disks. The gas swirling into a black hole emits a specific signature of X-rays. These object spectra have typical features that allow astronomers to distinguish them from other sources of light in space, such as neutron stars. In rare triumphs of technology, like with the Event Horizon Telescope, we are lucky enough to get a direct radio image of the disk, revealing a shadow or black spot in the center. That silhouette is the most direct evidence that the observed object's structure violates standard geometry. A black hole may also be detected thanks to a phenomenon called gravitational microlensing. This effect relies on the fact that gravity bends light. If a wandering black hole passes directly between Earth and a remote background star, it acts like a cosmic magnifying glass. It does not block the star. Instead, its gravity focuses the starlight, causing the background star to momentarily brighten and change its spectrum in a distinctive way. Admittedly, this method requires a precise alignment of factors to successfully work, making such detections rare events. Incidentally, it is important to remember that black holes are just one of the many possible endings in stellar evolution. They are the destiny reserved only for the most massive giants. For the vast majority of stars, the path leads to becoming a white dwarf or a neutron star. Every object in the universe is unique, and its path is determined by the complex interplay of gravity, mass, and composition. Studying the life cycles of stars allows us to better understand not only the boundless cosmos, but also our own existence. The connection is direct and physical. The carbon in our cells, the oxygen we breathe, the calcium in our bones, and the iron in our blood were not created on Earth. They were forged inside the burning cores of the stars we have discussed and scattered across the galaxy by the supernova explosions that mark their deaths. We humans are effectively a tiny part of this vast, all-pervading mystery, appearing for a brief moment to observe the universe that created us. We are the result of the long and complex evolution of stars and planets. And as our technology advances, allowing us to see deeper into the dark and further back in time, who knows what other amazing discoveries are waiting for us